In section 7.1, we're talking about systems of linear equations in two variables. So we have some types of linear systems, and there's three of them that we're going to cover. There's only three types. So you have an independent system that has exactly one solution pair, x and y, and that solution is where the two lines intersect. You have an inconsistent system that has absolutely no solution, and that's talking about parallel lines, because parallel lines will never intersect. Whenever you have an intersection of these two lines in this linear system, that's where you have a solution. And since you have parallel lines, you don't have intersections, which means you don't have any solutions. A dependent system has infinitely many solutions, because it's basically you have a line and then another line on top of the other line. So it's basically the same line. You have two equations that are describing the same line. So that means that if you have one line on top of the other, well, they're intersecting at every single point, and these lines keep going on forever. So you have infinitely many intersections, which means you have infinitely many solutions. So let's look at that as a graph. So here we have here's one equation, and here's another one. Now notice this is an independent system because they cross each other, or they intersect each other at one point, and that is right here. And so that is your solution, the 7 over 5 comma negative 11 over 5. That is the solution to that system. Now looking at this over here, where you have parallel lines, this is what we call an inconsistent system, because these two lines will never intersect, which means they will have no solutions. And then you have this one over here. This is a dependent system. You actually have two lines on top of each other, and they're intersecting at every single point because it's the same line. So they would have infinitely many solutions. So how we're going to solve this is when you have a independent system like this first one here, you'll have one solution. The two lines intersect at only one point. The solution is an ordered pair. When you have no solution, you're talking about parallel lines. It's an inconsistent system. So when we go to solve these, we will have no variables left. We'll have a false statement, and then we can say, hey, these lines are parallel and they're never going to intersect. Now when you have infinitely many solutions, you're going to have a dependent system. This means that when we go to solve this, we won't have any variables left over, but we'll have a true statement. And then we can say, hey, this is the same line, and they intersect at every point on the line. So we have infinitely many solutions. So how do you determine if an ordered pair is a solution to a system of a linear equation? Well, you just substitute that ordered pair into each equation in the system. Determine whether true statements results from the substitution in both equations. If so, the ordered pair is a solution. So you take the ordered pair and you plug it into both equations. If both equations come out with a true statement, then you can say that the ordered pair is a solution. But if you insert the ordered pair into one of the equations and it comes out to a false statement, but the other one comes out to a true statement, well, then it's not a solution. Both of the equations have to come out to a true statement in order for the ordered pair to be a solution. So let's look at this one. Determine if the ordered pair 5, 1 is a solution to the linear system. And there's your linear system. So we're going to label this one as equation 1 and equation 2. And let me actually write it on the outside there. Equation 1 and equation 2. Okay, so for equation 1, okay, so 5 plus 3 times 1 equals 8. So 5 plus 3 equals 8. So 8 equals 8. Okay, so the first one checks out. Okay, 2 times 5 minus 9 is equal to 8. Or sorry, 1. Okay, so that would be 10 minus 9 is equal to 1, so 1 is equal to 1. Okay, since both equations came out to a true statement, we can say that 5, 1 is a solution to this ordered or to this linear system. And this is what it would look like if we actually graphed the two equations here. And notice at 5, 1, that is where the two lines intersect. That's why it is a solution to that linear system. Okay, determine if the ordered pair 2, -3 is a solution to the linear system. We'll label this one as 1 and this one as 2. Okay, so we have -3 is equal to -2 minus 1, so -3 is equal to -3. That one checks out. And then for 2, we have 4 times 2 minus 3 times -3 is equal to 24. That will be 8 plus 9 is equal to 24. 17 is equal to 24. Okay, that is not true. So because one of the equations came out to a false statement, we can say 2, -3 is not a solution to this linear system. Now here's a graph of the two equations along with the point that they gave us, which was 2, -3. Notice how that point, at that point, they're not intersecting. It's only one line that is true, because this line falls on the first equation, but that point does not fall on the second equation, which is right here. So that's why it was true for one of them, but it wasn't true for the other one, because that point is only on one of the lines, it's not on the other one. So let's look at this one. Determine if the point on the graph represents a solution for the system below. Okay, well, here's our point right here. The solution to the system is where they intersect, which is right here, and that is not this point. So, no, it does not represent the solution. Determine if the point on the graph represents a solution for the system below. Okay, here's our point right here. Hey, that's where the two lines are intersecting. So yes, that point does represent the solution for that system. Okay, so let's look at methods and outcomes in solving these systems of linear equations. So there's three methods. There's a graphing method, a substitution method, and an addition method. And there's three outcomes. You can have one solution, no solutions, or infinitely many solutions. Now you'd want to use the substitution method when the coefficients in front of x or y is 1. And it's best to use the addition method when the coefficients of x and y is not 1. And we'll go through both of them. Solve the linear system by graphing. Okay, well, to do this, we need to get both of them into y equals mx plus b format. Okay, so for the first equation, so 2x plus y is equal to -8. I'm going to move 2x over to the other side. So y is equal to -2x minus 8. Okay, so here is the y-intercept. So that's at 0, -8, so right here. And then I need to go down 2 over 1. Okay, I had to change graphs to fit this on here. Okay, then I need to go down 2 and over 1 to right here. Okay, so, and then we're trying to draw a straight line between those 2 points. Okay, something like that. And then we'll go to the other graph. So let's do the other graph here, number 2. So x minus y is equal to -1. Okay, so we're going to have -y is equal to -x minus 1, and then change everything to a positive. Okay, so 1, 0. Then I need to go up 1 over 1. Okay, so looks like about was that -4, -2. I know that my graph is a little bit off. Here's what it should look like, and looks like where they intersect is -3, -2. Now I don't advise using the graphing method because of this right here. It looked like on my graph, it looked like -4, -2. So if you're doing this by hand, then you are leaving yourself room for error if you're doing this by hand. If you do this on a calculator or a computer, and you can clearly see the straight lines, unlike mine, this one shows -3, -2 for the solution for that linear system. Okay, now let's look at this one. We'll call this 1, we'll call this 2. So 1, 3x plus 2y is equal to 6. Okay, so I'm going to move the 3x over, divide everything by 2. So y is equal to -3 over 2x plus 3. Okay, so 3, 0. And then I need to move 1, 2, 3, 1, 2. So 3 down over 2. Okay, and then we'll look at the second one here. 6x plus 4y is equal to 12. I'm going to move that 6x over, divide everything by 4. So y is equal to -6 over 4. I'm going to take a 2 out of both of those. 3 over 2x plus 3. Okay, well notice, well that's the exact same thing I got over here. So that's the exact same line. So if it's the exact same line, then I have infinitely many solutions here. So we have infinitely many solutions. Then let's look at this one. We'll call this one 1. We'll call this one 2. Okay, for 1, we have 7x minus 2 is equal to y. Okay, so really it's already put into y equals mx plus b format. Oops. Okay, so -2 is my y-intercept, and I need to go down 7 over 1. It's going to go off the chart again. 1, 2, 3, 4, 5, 6, 7 over 1. That's about here. Okay, so we'll combine those two. Whoops. Okay, I know it's not very straight. Okay, so 5 minus y is equal to -7x. Okay, so -y is equal to -7x minus 5. Change everything to a positive. Okay, so now our intercept is 5. We need to go down 7, so 1, 2, 3, 4, let's see, 1, 2, 3, 4, 5, 6, 7 over 1. Okay, so draw those. Let me try to draw this one a little bit straighter here. Okay, so what we have here is we have two parallel lines. Okay, so since we have two parallel lines, that means that we have no solutions.